Here's the same problem that we've been seeing for a long time. You can tell because it's area 6. This is the 6th day I've been talking about area. I gave you the day off yesterday for me talking, because I thought we all needed a rest. Today, the thing that we want to look at is this antiderivative business. We've talked a little bit, very little bit. We just had one little introduction into finding an antiderivative. Find the antiderivative of x to the n is x to the n plus 1 divided by n plus 1. We add 1 to the exponent, divide by the new exponent. What we want to look at today is this part of this antiderivative relationship. We're looking for a capital F whose derivative is little f. I'm trying to find a function capital F such that f prime is equal to little f. That's what add 1 to the exponent, divide by the new exponent is about. But we want to think a little bit more about this. So capital F is an antiderivative of little f. That means little f is the derivative of capital F. That's what this statement says. Little f is equal to f prime, capital F prime. What this relates to, as far as things that we've looked at before, is that since little f is the derivative of capital F, the sign of little f tells us about the direction of capital F. So this is saying that the sign of little f gives the direction of capital F. Although it won't be much of an issue today for our purposes, this also tells us that the direction of little f tells us the concavity of capital F. Direction of little f gives the concavity of capital F. That's a thing that we've looked at before. Sign of the derivative tells you about the direction of the function. In this case, the curve that we're looking at is the derivative. Sign of this derivative tells you about the direction of the function. What this is telling, in these terms, we can interpret the definite integral and or the fundamental theorem of calculus is that when we integrate a rate of change over an interval, we find out how much the function changes on that interval. Capital F at B minus capital F at A is just how much the function has changed on the interval from A to B. A is where it starts, B is where it ended. So with this in mind, I wanted to summarize more. So what that means is that if capital F is increasing, that means little f is positive. If capital F is flat, that must mean that little f is equal to 0. And if capital F is decreasing, that means that little f is negative. This is the same thing what we've written before, but instead of writing f and f prime, I'm writing capital F. And instead of writing capital F prime, I'm writing little f, because that's the relationship we're exploring. So another way we could read this definite integral, or the fundamental theorem of calculus, with this relationship in mind, in the fundamental theorem of calculus, we could say the definite integral from a to b of the derivative of capital F. So here we are including that antiderivative relationship in the statement of the fundamental theorem of calculus. I'm just rephrasing the fundamental theorem of calculus with the capital F prime in it. So when we calculate the definite integral of the rate of change of a function, we calculate the definite integral of the derivative of a function, we find out how much the function has changed on that interval. The definite integral of the derivative of a function over the interval gives the change in the function over the interval. This will be a more useful way to think about the fundamental theorem of calculus in terms of chapter 5, where distance is equal to rate times time. In that framing, this capital F prime of x is the rate of change of the function. Dx is like time, and the capital F at b minus capital F at a, that would be distance or displacement. So here we have rate multiplied by time equals distance. So here is another way we can interpret the fundamental, we can write the fundamental theorem of calculus. Definite integral from a to b of f prime of x dx is f at b minus f at a. The way we interpret that is we say the definite integral of the derivative over an interval gives us a change in the function on that interval. If we integrate our rate over some interval of time, that will tell us our change in displacement. That will tell us our distance over that time. Any questions? I'm sorry, bro. Okay. Everybody looks all sad. because you only got 4 days of calculus this week. You're super disappointed. It's like, oh man, I wanted to come to calculus on Wednesday. Did everybody just show up and do calculus without me? That's what happens in my mind. Stuff our students are like, oh, nah, we're gonna have calculus anyway. And like everybody showed up, so hey guys, you want to do some calculus all on our own? And you're like, oh yeah. And then that's why I got the email that says, dude, we had calculus on Wednesday. We gave the final, everybody got an A. So I think everybody got an A in the class. Dang. That's only worked like 7 or 8 times on me before. And now that I've said it out loud, you're like, oh shit, we could have done that. I'm like, oh, totally. Y'all are in control. You could have just like showed up here, said we had the final, everybody got 100%. But now you're stuck with me again. So if you would recall, if you would recall, on the discussion on Canvas, this is the function that we wanted to think about. Today, so we got this polynomial function. We've got zeros at 0, 1, and 3. So this is a polynomial function with zeros at 0, 1, and 3. Since we've got a polynomial function with these 3 zeros and a positive leading coefficient, we know what this graph must look like. Since we also have Desmos right in our pocket, we know what this graph should look like. So what we notice is that there is like, it goes up, down, and then up again, unsurprisingly. What we notice is if we actually graph it, is that there's a small bump from 0 to 1, kind of a bigger valley from 1 to 3, but then it's just predictable polynomial stuff. So in case you missed it, the exercise was to calculate a couple of definite integrals. So I actually calculate the integral from 0 to 1 of f of x dx. I also asked you to use the fundamental theorem of calculus. So you need to find an antiderivative of the function. That's why I gave you both forms, because we can find the antiderivative of this multiplied out form, the standard form. We don't know how to find the antiderivative of a product. All we know right now is we have to multiply that stuff out and then do a term at a time. But I also mentioned that your calculator can do this thing. And the button that we're going to want is the math button, which is funny because it's a calculator. They're all math buttons, but there's one labeled math. You can see right here, math. The definite integral command is down here in the math menu, number 9, FNINT. If you want to calculate an FN integral. Look at derivative. They're like positive about derivatives. It's not like function derivative. It's not FN derivatives, but it's definitely FN integrals. FN integral. The syntax that you put in is the function, comma x, comma a, comma b. It's 4 things. You have to tell the calculator what function you want to integrate. So x cubed minus 4x squared plus 3x. Then we have to say the dx part. Integrate this function dx from 0 to 1. And since this is a polynomial, we know we're going to get a fraction. So if we want a fraction, we can use the math button and convert it to a fraction by putting that command at the end. And we get 5/12. Then I asked you to do the integral from 1 to 3. In which case we could use the same command. So I'm just going to press second entry to get the same thing and change the starting from 1 and going up to 3. And then something interesting happens here. We get a negative value. Why do we get a negative value is the question. So first, let's write this down, -8/3. So when we look at this graph, we know that the definite integral is supposed to tell us the area under the curve and above the interval in the x-axis. Under the curve and above the interval. So what is this area of this little bump up here? Which area is, how much is this? I'll call that A1. How much area do we have there? Well, that's the area under the curve f of x above the interval from 0 to 1. So that's the definite integral of f of x from 0 to 1, and that was 5/12. When we calculate the integral from 1 to 3, we're supposed to get the area under a curve and above the interval. But things are backwards because the function is negative from 1 to 3. So when we integrate from 1 to 3, the function is negative, and what happened to the definite integral? The definite integral is negative. So the area if I ask what the area is between the function and the x-axis, then we would say 8/3. The definite integral reports a negative value because the function or the graph is negative. F of x is negative. The definite integral is negative because f of x is below the x-axis. F of x is below the x-axis. So little f is negative. So capital F is decreasing. The negative 8/3 is how much capital F decreased. This is the connection between the area stuff that we're doing now and the sign, direction, concavity stuff that we did before. The derivative is negative, so the function is decreasing. The area tells you by how much the function decreased. capital F, will be 1/4 x to the fourth minus 4/3 x to the third plus 3/2 x squared plus some constants. So if I evaluate this function at 3, we get -9/4. And if we evaluate this function at 1, we get 5/12. And if we take -9/4 minus 5/12, we get -8/3. Sign of the derivative tells you the direction of the function. The area tells you how much increase or decrease we see. When we find the definite integral of a function that goes negative, when we find the definite integral of a function that goes negative, we end up with a negative value. That makes sense because that tells us that the antiderivative is decreasing. And so the change in the values at the endpoints should be negative because the function is decreasing. The other definite integral that I asked you to calculate was the overall definite integral from 0 to 3. The definite integral from 0 to 3 is the -9/4. -9/4 is the definite integral from 0 to 1 plus the definite integral from 1 to 3. It makes sense that we should just add these areas up because that's how we find total area. We just add up all the areas. That was the whole idea behind doing this calculation. Calculate the areas of a bunch of rectangles and add them up. So if we take the positive 5/12 area from 0 to 1 and add the -8/3 area from 1 to 3, we get -9/4. Questions? 5/12 is the integral from 0 to 1. -8/3 is the integral from 1 to 3. Questions? Yes.
Looks like a real world. Like it's cool, but
No, it's fine.
I'm just curious, like,
Like, where we're actually finding antiderivatives. Finding antiderivatives, never. I'll just put that out there. After you get through this class, if you take Calc 3, then you might have to find some antiderivatives, right? It depends. If you end up in my Calc 3 class, or actually Calc 2, this is Calc 1. So definitely in Calc 2, you're gonna be finding some antiderivatives. And then in Calc 3, you're gonna be finding some antiderivatives. Because Calc 3 is just Calc 1 and Calc 2 with more variables. Instead of f of x, you have an f of xy. That's it. But after you get through that, until your kids are in calculus, you won't have to find any more antiderivatives. Big caveat, unless you become like a calculus teacher. If you become a calculus teacher, then you're like, oh, dude, you wouldn't say we wouldn't have to do this anymore. My God, you chose to be a teacher, so you're signing up for that. But never. Like if you're at your job at like I don't know, whatever company we've decided is going to fly to Mars, and you're about to find an antiderivative by hand, you're about to get fired because your boss will be like, oh, what are you doing? You're like, oh, I'm finding some antiderivatives. And they'll be like, oh, motherfucker, we have like a bunch of computers that can do that stuff for us. What are you talking about? Finding antiderivatives by hand. At that point, you need to lean into it and be like, oh, dude, I am quirky. I am a quirky, eccentric genius. That's why you hired me. You wouldn't understand. Just play it off like that. They'll be like, oh, okay. You know what I mean? But no, you won't have to. But it really restricts out. The important thing is what this integration represents. It's how we think about doing this area thing where we're trying to calculate something, but one of our factors is continuously variable. That's the core of what we're trying to do. This is all this finding antiderivatives and stuff. That's just kind of like a bunch of bullshit that gets in the way. So, to answer your question, which is perfectly valid, probably never, like from a practical standpoint. But that also isn't like the point of what we're trying to do right now. Does that make sense? Does that seem fair? I just want to be transparent because I realize that a lot of times I heard it a lot when I was going through algebra. I don't know if we still do this as algebra teachers. It's like, oh, you're going to need to know this in calculus. And then how many people have heard that? You're going to need to know this in calculus. As if like calculus was going to be some big revelatory thing. And you get to calculus, I'm like, all right, now we find out. And then you're like, well, why do we need to know this? And you're in college now, so your professor's like, oh, fuck, I don't know. You tell me. I hope that's fair enough, right? Because there are all kinds of dick answers to that question. Like at one point, like there's a bunch of pre-med students and they're taking a physics class or some shit. And the pre-med students are like, oh, we're going to be doctors. Why do we need to know physics? And the physics professor's like, oh, physics saves lives. And they're like, well, how does it do that? So, well, it keeps people out of medical school. That's pretty harsh. I mean, like, funny, because we don't know anybody involved in this scenario, but that's pretty fucked up. So I decided when I heard that joke, after I got done laughing at it, I was like, well, you know what? I'm just going to be honest with the students and say, hey, we're just trying to have this overall conversation. And I try to be honest with why we had that conversation and point out the fact that, yeah, I'm going to ask you to do this, and it's going to make a difference in what the score that you get in this class, but it's not because you're going to be doing this in the future. It's something that we have to do right now. If you don't like that, think of this as lateral raises, right? Everybody know what a lateral raise is? I think I've used this analogy before, but a lateral raise is when you have a weight in your hand and you hold it out to the side like this, and then you put it down. And then you pick it up again, and then you put it down. And then you pick it up again, and then you put it down. Because your trainer says, do that. And no one, when they're doing that, it's like, oh, why do I have to do this? This is not how we pick stuff up. Because it's not how you pick stuff up. I'm like, oh, let me grab my calculator. It's just, you just grab it like this, right? This is the reason that your arm has this joint. So it's like, oh, I don't want to put that much torque on my shoulder. I'll just do it on my elbow, right? So I'll use all these, but it makes your this whole structure stronger. And so you focus on that one thing. You focus on this one thing, it makes your overall picture stronger so that we can have more important conversations later. Because the other thing that a lot of people don't tell you is what happens after calculus. And the answer is math. Math happens after calculus. Even though we have pre-calculus, it's like calculus is some kind of like end game. Calculus is not the end. Calculus is the end of the beginning. After this is where you start doing math classes. That makes sense? I know it's really disheartening to struggle through all these math classes and have your calculus teacher be like, oh, you haven't been in math classes yet. And you're like, oh, motherfucker, I've been doing math classes for like 14 years. He's like, oh, yes, and now math begins. So right now we're still learning the language so that we can have conversations later. And most importantly, one of the things that's really difficult about this is that this has already been decided. The interesting questions are the ones that we haven't even asked yet. Like that's where the interesting questions are. This is the path to unlocking the secrets of the universe. You don't get to unlock the secrets of the universe without speaking the language of the universe. And this is how we've decided to encode the language of the universe. Does that make sense? That's an excellent question, especially when the answer is really just like, oh, never. And then I have to talk about it for like 10 minutes. That's because you fucked up by taking my class. Instead of having just a professor who would be like, oh, never. See you tomorrow. I'm like, oh, never. But that's an interesting question. Let me talk about it for the next 10 minutes. You're like, oh, fuck. What have I done? You know what I mean? I think the other thing is I never wanted to be that teacher that got mad when the students asked, what the fuck? Like, why are we doing this? Because it's a legitimate question. And I hope y'all ask yourself that all the time because you're making this huge investment. The money is one thing. Money comes and goes, right? I know we all need money to live because Jeff Bezos needs to fly some of his friends to space or some shit, but this is a huge investment, not just of money, but of time. The money, theoretically, you can make back, right? Over the course of your lifetime, you're supposed to be able to make the money. That's how we sell you on this little endeavor, right? But this is going to be 4 to 10 years of your life. That time doesn't come back. If you feel like this is not valuable to you, go do something else. I can't stress that enough. If you feel like every time you go into a class, you feel like you're just wasting your time and you would rather be doing something else, go do something else. You are 100% free to do that. Y'all are adults. For the most part, I didn't look up your ages, but as soon as you're 18, your signature is legal and no one can be telling you what to do with your time anymore. So if you're like, oh, this is not valuable to me, I don't see the value in this, that's fine. That's okay. Does that make sense? It is an absolute lie that we tell to young people, which is the most fucked up thing that we do. One of the on the long list of fucked up things that we do as a society is that we tell young people when they don't know any better and when they're in high school that you have to go to college. You have to go to college. How many of you got that message when you were in high school? You have to go to college. How many people above the age of 25 have a bachelor's degree or later, like a bachelor's degree? What percentage of people above the age of 25 who could reasonably have done it have a bachelor's degree? It must be a lot, right? Because you've been told you have to do this to be successful. What percentage? It must be a lot, right? Like 70%? 50%? Try like 30. 30%. So 70% of the people above the age of 25 are losers that are never going to get a job. Last I checked, a lot of them have fucking jobs. You know what I mean? You got to be doing this because you want to be doing this. Because there has to be some kind of interior motivation for you to do this. If you're just doing this because someone told you to do it, when you finish, you're like, ah, that was a waste of time. And if that's what happens at the end, you finish your graduate degree, your bachelor's degree, and you're like, oh man, what a waste of time. Fucking, that's on you. You fucked up. Because I'm trying to tell you what I'm selling. This is calculus. We're trying to have conversations, more nuanced conversations later on that are done in this language. That's what I have on offer. If you're like, I don't care about that. I'm like, oh, that's cool. I won't even be offended. If you want to offend me, you're going to have to do a lot better than that. You know what I mean? The investment isn't the money. The investment is the time. You can't get that back. All right. That is going to do it for today. Sorry for like pontificating at you. I do that all the fucking time. So I'm not sorry. I'm going to do it again. If I like never did that again, then that would demonstrate being sorry. But it's actually not going to lead to a change in behavior. So, God, I'm a dick. That's it for today. I will see you all on tomorrow. Everybody have a good day. And thank you for playing.